Any questions about Chinese remainder theorem, Euler phi function? Any of the homework problems that you'd like me to go over? No? Okay.
Professor,
Yes.
good morning. Can you do a problem about the Chinese remainder theorem again, just to refresh?
Sure. So there are two forms of the Chinese remainder theorem. So CRT, Chinese remainder theorem. So the first form, which is theorem 2.9 in the book, so you have positive integers m and n, and there exists an integer x such that you can simultaneously satisfy the congruences x congruent to A mod m and x congruent to B mod n, if and only if A is congruent to B modulo the greatest common divisor of m and n. And if this set of congruences has a solution, if x is a solution, then y is also a solution. If and only if x is congruent to y modulo the least common multiple of m and n, right? So square brackets mn is the least common multiple of m and n. And then it's natural to ask, if you can solve two congruences, when can you solve three or four or any finite number? And in one particularly important special case, that's theorem 210, it says the following: if we have k congruences, x congruent to A1 mod M1, x congruent to A2 mod M2, down to x congruent to A sub k mod M sub k. So if you have integers A1 up to A sub k, and M1 up to M sub k, so these are integers, but the M sub i's are positive integers, and the moduli, the m's, are pairwise relatively prime. So the greatest common divisor of mi and mj is 1 for all I different from j. So then there exists an x satisfying these congruences. So if you have k linear congruences and the moduli are pairwise relatively prime, you can always solve this system of congruences. And if x is a solution, then y is also a solution if and only if x is congruent to y modulo the least common multiple of all these moduli, but because they're relatively prime, the least common multiple is just the product of the moduli. So these are two forms of the Chinese remainder theorem. And let's look at some of the homework problems. It's just numbers 1 to 6. So let me choose, for example, number 3. Unless someone prefers another one. So this is section 2.4. Exercise 3. So we want to solve x congruent to 5 mod 12 and x congruent to 8 mod 10. Is there a solution? And if there is, find them all. Well, notice that the greatest common divisor of the moduli is 2. And 5 is not congruent to 8 modulo 2. Therefore, there's no solution. Right? The necessary and sufficient condition for two linear congruences to have a solution is that these right sides, 5 and 8, the difference is divisible by the GCD, and 3 is not divisible by 2. So there's no solution. Let's look at exercise 2. Any questions about that? Exercise 2, we have x congruent to 5 mod 9 and x congruent to 8. Sorry, x congruent to 5 mod 12 and x congruent to 8 mod 9. So in this case, the greatest common divisor of 12 and 9 is 3, and 5 is congruent to 8 mod 3. So therefore, there exist solutions. So one way to find a solution is just to argue as follows. If x is congruent to 5 mod 12, then x is an integer of the form 5 plus 12 times y for some integer y. So x congruent to 8 mod 9 means that 5 plus 12y has to be congruent to 8 mod 9. So this is just one congruence, 12y congruent to 3 mod 9. 12 is the same as 3 mod 9, 3y congruent to 3 mod 9. So y is congruent to 1 mod 3. Right? If 3y is congruent to 3 mod 9, y has to be 1 mod 3. So y is some number of the form 1 plus 3z for any integer z. And what is x? X is 5 plus 12y. That's 5 plus 12 times 1 plus 3z. This is 5 plus 12 is 17 plus 36 z. And so first of all, 17 is a solution. 17 minus 5 is 12. 17 minus 8 is 9. So 17 is a solution. So the set of all solutions, it's all x congruent to 17 mod 36. And notice, of course, the least common multiple of 12 and 9 is 36. So this is the answer to the question. All solutions are all numbers that are congruent to 17 mod 36. All right. Any questions about this? Let me do one more.
Good morning, Professor. Do you have time to go over to another problem?
Yeah, which one?
Section 2.3, page 60, number 8.
Section 2. Okay, so let me do one more with the Chinese remainder theorem, and then I'll go and do that one.
Okay, thank you.
So this is still section 2.4. Let me look at exercise 4. So we have two linear equations of the form 2x congruent to 1 mod 5 and 3x congruent to 4 mod 7. And we want to find all simultaneous solutions of these two congruences. And I can say, well, we can't apply the Chinese remainder theorem directly, because in the Chinese remainder theorem, we had congruences that look like x congruent to A mod m, x congruent to b mod n, and the coefficients of x's in both cases were 1. And here the coefficients are 2 and 3 respectively. On the other hand, we can solve each of these equations separately and then apply the Chinese remainder theorem. So 2x congruent to 1 mod 5, if you multiply by 3, this is the same as x congruent to 3 mod 5. So every solution of this congruence is the solution of this congruence. And if we solve the congruence 3x congruent to 4 mod 7, that's the same as, let's see, what multiple of 3?
Multiply by 5. 5.
5 doesn't work because 15 minus 4 is 11, but 6 works. If you look at x congruent to 6 mod 7, 3 times 6 is 18. 18 minus 4 is 14. 14 is divisible by 7. It's 7 times 2. So this system of congruences is the same as this system of congruences. And we can apply the Chinese remainder theorem to this. The greatest common divisor of 5 and 7 is 1, and 3 is congruent to 6 mod 1. Everything is congruent to everything mod 1. So this system of congruences has a solution, and I won't go through the solution, but once we've reduced it to this form, the method that we used in the previous problem always works, and we'll get a solution of this. Okay. And there will be a unique solution modulo 35. In fact, if you go through the work, I think you'll find that the set of all solutions are all x congruent to, let's see, 13 mod 35 is the solution, because 13 minus 3 is 10 is divisible by 5. 13 minus 6 is 7 is divisible by 7. And the solution is a congruence class modulo the least common multiple of 5 and 7, which is 35.
Professor.
Yes.
Oh, I had my mic on mute, my bad. I have a question. When I think it was Ebony asked if we can multiply the second congruence by 5. Like, it's not possible to say, like, for example, if we multiply by 5, the 3 will become 15.
What is the second congruence? You mean this one?
I mean, no, 3x congruent to 4 mod 7.
Yes.
That one. If we multiply by 5, we cannot say like the 3 becomes 15, and that will have a remainder of 1.
So
And
15x is if you multiply by 5, 15x
mhm,
is congruent to 20 mod 7.
yeah, and
15 is 1 and 20 is
it's
6. So this is the same as x congruent to 6 mod 7.
okay, so that works too, right? Yeah, okay, she was
No,
right.
no, I mean,
Yeah.
I mean, it's not that it works too. I mean, you're saying the solution of this congruence is this, and this, you just showed one way to do it. I just wrote down the answer. I didn't tell you how I got it, but it doesn't matter. This is the solution.
No, I was just asking because when she said to multiply by 5, you say that that was not possible. So I want to make sure that it's okay to do it that way.
Oh, yeah, yeah. If
Okay,
it gives
thank
you the
you.
right answer, it's okay.
Thank you, Professor.
Okay, section 2.3, which exercise did you ask about?
Number 8 from page 60.
Number 8. So we want, this is a proof. Prove that if M divides N, then phi of M divides phi of N. So you can prove this in several ways. First, we can recall one formula that for phi of N is equal to N times the product over all the primes that divide N, 1 minus 1 over P. And phi of M is the product is M times the product, I write a letter Q, all primes Q that divide M, 1 minus 1 over Q. Actually, let's also recall the following. Suppose N is a product of primes, say it's P1 to the R1, P2 to the R2, up to PK to the R sub K. Right, this is just writing N as a product of powers of primes. And M divides N. So M, if a prime divides M, it divides N. So M is going to be some number of the form P1 to the S1, P2 to the S2, P sub K to the S sub K, where these exponents, S sub I, they could be 0. It could be there's a prime that divides N that doesn't divide M, but S sub I can't be any bigger than R sub I. So this is because M divides N. Every prime power that divides M has to divide N. So remember, for a prime power, phi of any I, P sub I to the Ri is P sub I to the Ri times 1 minus 1 over Pi. That's phi of a prime power. And phi of N, because phi is multiplicative, this is the product. I goes from 1 to K, phi of P sub I to the R sub I. Right? So we need to know the basic facts about the Euler phi function. This is phi of a prime power, and phi is multiplicative. So if N is a product of distinct prime powers, phi of N is the product of phi of those prime powers. which is phi, which is the product, I goes from 1 to n, p sub I to the r sub I, 1 minus 1 over pi. And phi of m is the product. I goes from 1 to k, phi of pi to the si, which is the product. I goes from 1 to k, pi to the si, 1 minus 1 over pi. So if you divide phi of n by phi of m, what happens? So for all the si's which are positive, these cancel, and this is a product of just pi to the ri minus si. I goes from 1 to k. This is an integer. So phi of n divided by phi of m is an integer. That means phi of m divides phi of n. So that is one way to prove this. Okay. Let me prove the theorem of the day, which is Euler's theorem. So this is section 2.5. Euler's theorem, which says the following. Let m be a positive integer, and let a be an integer relatively prime to m. That is, the greatest common divisor of a and m is 1. Then, if I take a and raise it to the power phi of m, this is always congruent to 1 mod m. So this is the formula that is Euler's theorem. And there's a special case. So this is theorem 212. The special case is called Fermat's theorem. If the modulus m is a prime p, then phi of p is always p minus 1. And so a to the power p minus 1 is congruent to 1 mod p. So before I prove the theorem, let's just look at some examples. Suppose I take p equal to 5. So I'll make a little table. A and a to the p minus 1. Well, in this case, p is 5. So p minus 1 is 4. So I'm going to take a and then a to the 4th power mod 5. So what are the numbers relatively prime to 5? 1, 2, 3, and 4. So if I take 1, 1 to the 4th is 1. mod 5. If I take 2 to the 4th is 16, is congruent to 1 mod 5. If I take 3 to the 4th, 3, 9, 27, 81 is congruent to 1 mod 5. If I take 4, what is 4 to the 4th? 4 to the 4th, which is 2 to the 8th, is 256. Take away 1 is 255. So this is congruent to 1 mod 5. So this is an example of Euler's theorem. So, for example, 3 to the 6th is congruent to 1 mod 7, because 3 is 7 is a prime, 3 and 7 are relatively prime, and phi of 7 is 6. So I know this is true without doing any multiplication. If I want to just check numerically, what is 3 to the 6th? So what are the powers of 3? 3, 9, 27, 81, 243, 729. So 3 to the 6th is 729. If I take away 1, I get 728. And I can see this is divisible by 7. This is 7 times 104. So 3 to the 6th is congruent to 1 mod 7. Any questions about this? What the theorem says? I still have to prove it, but okay, so how do I prove Euler's theorem? So let's just recall a few terms about congruences. So if we have m a positive integer, a complete system of residues modulo m is a set of m integers, say a1 up to am, such that every integer b is congruent to a sub I for some a sub I, let me just call this S, for some ai in the set. So that is a complete system of residues modulo m, or a complete set of residues, both terms are used. The complete set of residues mod m is just m integers, one from each congruence class modulo m. For example, if I take the set of integers 0, 1, 2, 3, up to m minus 1, this is a complete set of residues. Now, there are phi of m is the Euler phi function. Congruence classes relatively prime to M, and what is called a reduced set of residues modulo M is a set of phi of M integers. Say R1, R2, up to R sub phi of M. I'll call this R, such that every integer B that is relatively prime to M satisfies B is congruent to R sub I mod M for some integer R sub I in the set R. So for example, the set 1, 5, 7, and 11 is a reduced set of residues modulo 12. Right? Phi of 12, you know, is 4, and any integer relatively prime to 12 will be congruent to one of these. But this is not unique. For example, if I take the set 13 minus 7, 31, and minus 1, this is also a reduced set of residues, modulo 12. 1 is congruent to 13, 5 is congruent to 12, 7 is congruent to 31, and 11 is congruent to minus 1. If every number that's relatively prime to 12 is congruent to one of these four, it's also congruent to one of these four, and conversely. So there are many, infinitely many complete sets of residues and reduced sets of residues modulo M for any M. And we also know the following. If we have two numbers, if A and M are relatively prime and R and M are relatively prime, then AR, the product, is relatively prime to M. Because if there were a prime P that divided M and AR, if a prime divides a product, it divides at least one of the factors. It can't divide A because A is prime to M. It can't divide R because R is prime to M, so there can't be any such P. So if you take the product of two numbers relatively prime to M, you get another number, another integer that's relatively prime to M. So now we can give a proof of Euler's theorem. Suppose we let R1, R2 up to R sub phi of M be a reduced set of residues mod M. Let A be an integer that's also relatively prime to M. So AM is congruent to 1 mod M. So it follows that AR1 is relatively prime to M because each of these numbers is relatively prime to M, and you multiply it by a number that's relatively prime to M, you get a product relatively prime to M. So A times R1 is relatively prime to M. And in fact, if you multiply any one of these numbers, R sub I by A, ARI is relatively prime to M for all I going from 1 up to phi of M. So, but if ARI is relatively prime to M, for all I, there exists some integer sigma of I between 1 and phi of M, such that A times R sub I is congruent. This is relatively prime to M, so it has to be congruent to one of the numbers in the reduced set of residues, or let's say sigma of I mod M. And if Ri is not congruent to R, let's say, so ARI is congruent to ARJ mod M, if and only if RI is congruent to RJ mod M. Because if M divides, if this congruence hold, M divides the difference, M doesn't divide A, M is relatively prime to A, so RI is congruent to RJ mod M. So the values sigma of 1, sigma of 2, up to sigma of phi of M, these are different integers. Because for every I, you get a sigma of I, and the sigma, the ARIs are different elements of this set. So this is just the set of all numbers from 1 up to phi of M. Sigma is just some permutation of 1 up to M. So what I get is that if I take the product AR1, this is all mod M, AR1 is congruent to R sigma of 1 times AR2, that's R sigma of 2. AR3, that's R sigma of 3, up to AR sub phi of M, this is R sigma of phi of M. So this is just a product of elements of this set, but the sigmas are distinct. This is just some permutation of 1 up to M. And what I have on the left-hand side, I have a factor of A phi of M times. This is A to the power of phi of M times R1, R2, R3, up to R sub phi of M. And what I have on this side is the same product of integers, R1, R2, R3, up to R sub phi of M mod M. So A to the phi of M times this product is equal to the product, which is like 1 times the product. But this product R of the R's is relatively prime to 1. So I can cancel it, and I get A to the phi of M congruent to 1 mod M. And that is a proof of Euler's theorem. So this is, again, one of the fundamental results in number theory. Let's just look at another numerical example. So let's see, 5 and 12 are relatively prime. Phi of 12 is 4. So by Euler's theorem, 5 to the 4th has to be congruent to 1 mod 12. If we wanted to check, what is 5 to the 4th? 5, 25, 125, 625. 5 to the 4th minus 1 is 624. If I divide 12 into 624, it goes 52 times. This is 12 times 52. So if you didn't know Euler's theorem, you just do the calculation and you get this result. Here's another example. 83 to the 512th power is congruent to 1 mod 1024. Now, this you don't want to check by hand. I mean, this is, you can't take 83 and raise it to the 512th power, right? I mean, it would take you a year just to multiply 83 by itself 512 times. I don't know that your computer, unless you know how to do something special to it, could actually do that. But we know this is true. Why is this true? Because if I take m to be equal to 1024, which is 2 to the 10th, phi of m is phi of 2 to the 10th, that's 2 to the 9th, which is 512, 83 and m are relatively prime. 83 and 1024 have no factor in common. So this is simply saying that 83 to the phi of 1024 is congruent to 1 mod 1024. So we know this is true, even though we can't write this out. Actually, Maple can write it out. Here is 83 to the 512th power. Pretty big. Not sure you would want to do that by hand, but Maple actually could do it. I'm surprised. Suppose I subtract 1. Oops. That's not what I want to do. I have this number, and I subtract 1. And I take this number, and I divide it by 1024. And I get an integer. So, yeah, you could verify this in Maple, I guess. Okay. Any questions about this? It is impossible to overemphasize this. Now, one of the reasons why Euler's theorem is so important is because it has an interpretation and application in algebra, in group theory. And I would be remiss if I didn't explain that. So I shall. So this is some group theory. So remember, a group is a set G with a binary operation. It's usually written as either multiplication or addition, such that the following properties hold. First of all, the operation is associative. I'll write the operation as multiplication, but same as addition. If you take x, y, you can multiply them and multiply that by z. That's the same as x times y, z for all elements x, y, and z in the group. There exists an identity E in an element in the group, which is the identity, such that x times E and E times x equals x for all x in the group. If you think about the real numbers under multiplication, the identity is the number 1. If you think about the integers under addition, or the real numbers under addition, the identity is the number 0. For all elements in the group, there exists an element y in the group, such that x, y, and yx equal the identity. So anything that satisfies these properties is a group. And an abelian group or a commutative group the words mean the same thing, is a group G such that the order of multiplication doesn't matter. X, y equals yx for all x and y in the group. So the integers under addition, the binary operation of addition is an abelian group. The integers under multiplication are definitely not a group because there are no inverses. The identity is the integer 1, but there's no inverse of 2. 2 times a half is 1, but a half's not an integer. The congruence class is modulo m under addition. This is an additive abelian group. If I take z mod mz star, so this is a set of all congruence classes a plus mz, where a and m are relatively prime. This is a group under multiplication. This group has m elements. This group has phi of m elements, where phi is the order phi function. And If G is a finite group, what is called the order of G is just the number of elements in G. And the number of elements, another word for that is cardinality, or the cardinality of G. But it means the same thing. A subgroup of a group G is a subset of G, a non-empty subset, that is itself a group. So for example, if I take Z to be the integers under addition, and I take H to be the even numbers under addition, H is a subgroup of G, because the sum and difference of two even numbers is an even number. Every even integer is an integer. So 2Z is a subgroup of Z. These groups are infinite. If I take, for example, Z mod 6Z, this is the set of congruence classes mod 6. It consists of 6 elements. Each element is a congruence class. So the set of congruence classes mod 6, this is an additive abelian group. If I take H to be just the two congruence classes 0 and 3 plus 6Z and 6Z, this is closed under addition because 3 plus 3 is 6 is the same as 0. This is a subgroup. And notice the order of G is 6. The order of H is 2, and 2 divides 6. There's one other definition I need, which is that of a coset. Let G be a group, H a subgroup, so let G be a group, H a subgroup, and A an element of G. What we define as a coset is, and it's written A times H. What this means is this is the set of all elements of the form A times X, where X runs through H. So X is a subgroup, H is a subgroup. Take every element of the subgroup, multiply it on the left by A, and we get a coset. This is also called a left coset because I'm multiplying on the left by A. I can also multiply on the right by A. That would be a right coset. But unless the group is abelian, they don't have to be the same. So we have a group, a subgroup, and a coset. So I'm going to give a group theoretical proof of Euler's theorem. And first I need to prove an important result about groups called Lagrange's theorem. If G is a finite group and H is a subgroup of G, so G is a finite set, so H is a finite set, then the order of H divides the order of G. So here we had an example. We had a subgroup. We had a group of congruence classes mod 6. The order of the group is 6. H consists of 2 congruence classes. It's a subgroup, has 2 elements, and 2 divides 6. You couldn't have a subgroup of this group with 4 elements because 4 doesn't divide 6. So the proof. So we have sort of a picture. Here's the group G. And in that group G, we have a subset H, which is a subgroup. So let A and B be in G. We have cosets AH and BH. They're also subsets. These are cosets. They're also subsets of G. And I claim that if 2 cosets intersect, so if the intersection of those 2 sets is not empty, then AH equals BH. So if 2 cosets intersect, they're in fact equal sets. So if AH intersect BH contains some element Z, then Z is in both of those sets. Z is in AH and Z is also in BH. But to say Z is in AH means Z equals AX for some X in H. And to say that Z is in BH means Z is equal to BY for some Y in H. So AX equals Z, BY equals Z, AX equals BY. And because H is a subgroup, I can write, so I can multiply by Y inverse. So I have AX Y inverse is BY times Y inverse, which is B times Y inverse, which is B times the identity is B. So B is equal to A XY inverse, and XY inverse is in the subgroup because X and Y are in H. So H is a subgroup. It contains the inverse of each of its elements and is closed under multiplication. I'll call this W, or I'll call it W here. So this is A times W for some W in H. So for all H in H, B times H is A W times H. This is an element in the coset AH. And that's true for every element H in the subgroup capital H. So BH is a subset of AH. So if these two cosets intersect, BH is contained in AH, and there's a symmetric argument. You have to write it out. AH is contained in BH, so AH equals BH. So what this says is that in any group G and any subgroup H, the left cosets are pairwise disjoint. If you take two left cosets, if they're different, they in fact have no element in common. So this proves that the cosets of a subgroup H are pairwise disjoint. So suppose the group is finite. So I have H, which is the coset EH, and I have a collection of subsets, each of which is a coset. Moreover, every element A in G belongs to some coset. For example, A is in the coset AH, because H contains the identity and A is equal to A times E. So if I look at all of these cosets, there only can be finitely many because G is a finite group and these are finite subsets. Moreover, if I take a function f from A to AH by f of x equals AX, this function is 1-to-1 and onto. So this establishes a 1-to-1 correspondence between H and AH. So for all of these cosets, the cardinality of all of these cosets is the same for all of these AIs. Suppose we let G mod H be the set of left cosets of H and G. Then the number of left cosets, so this is the cardinality, the number of left cosets, times the size of each coset is the size of G. And that's the end of the proof. These are all positive integers. H times something equals cardinality of H times some integer is the cardinality of G. So cardinality of H divides cardinality of G. That's the proof. So this really just takes about a third of a page in the book to write out, but this is really something that's worth investing your time to try to understand. But this is Lagrange's theorem. It says that the cardinality of a subgroup of a finite group always divides the order of the group. Nothing else is possible. let's go back to our elementary bits of group theory. That G be a group, and I always prefer to write groups multiplicatively, but I can use a plus sign in addition if I like. Let A be an element of G, and let, I'll write it A in brackets, be A, the set of all powers of A. A to the K, K and Z. So what does this mean? So A to the first power is A. A squared is A times A. A cubed is A times A times A, and so forth. A to the 0 is, we define that to be the identity. A to the power minus 1 is the inverse of A. A to the minus 2, this is A inverse squared, A inverse times A inverse. A to the minus 3 is A inverse cubed, A inverse, A inverse, A inverse, and so forth. And we have the multiplication rule, A to the K times A to the L is A to the K plus L for all integers K and L. So this set of all powers of A, positive and negative and 0, is a subgroup of G, which is called the cyclic subgroup. Generated by A. It's always an abelian subgroup. And we say that a group G is a cyclic group if there exists an element A in G such that the subgroup generated by A is all of G. So for example, in the positive real numbers, if I let G be the set of 1, 2, 4, 8, 16, and so forth, and a half, a fourth, a 16th, an eighth, a 16th, and so forth, this is exactly the cyclic subgroup generated by 2. Because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the minus 1 is a half, and so forth. This is all the positive and negative and zeros powers of 2. So this is a multiplicative group, and it's cyclic, and 2 is a generator. What's another example? Suppose I take Z mod 5Z. This is the additive group of congruence classes mod 5, but this is the group of congruence classes relatively prime to 5, 1 plus 5Z, 2 plus 5Z, 3 plus 5Z, and 4 plus 5Z. So this is a multiplicative group with 4 elements. If you wanted to write out the multiplication table, I'll just write 1, 2, 3, 4 as a shorthand for these congruence classes. 1 times everything is 1. 1 is the multiplicative identity. 2 times 2 is 4. 2 times 3 is 6, which is 1 mod 5. 2 times 4 is 8, which is 3 mod 5. 3 times 2 is 6, which is 1. 3 times 3 is 9, which is 4. 3 times 4 is 12, which is 2. 4 times 2 is 8, which is 3 mod 5. 4 times 3 is 12, which is 2. 4 times 4 is 16, which is 1. This is the multiplication table. What is the cyclic subgroup generated by 2 plus 5z? So it's the set of powers. I have 2 plus 5z, 2 plus 5z squared, which is 4 plus 5z, 2 plus 5z cubed, which is 8 plus 5z, which is 3 plus 5z, 4 plus 5z cubed. See, 4 cubed is 64, which is 1 plus 5z. 4 plus 5z to the fourth. It brings me back to 2. These powers then just start to repeat, but you notice these powers of 2 plus 5z, I get the whole group. So this group with 4 elements is a cyclic group, and 2 plus 5z, that one particular congruence class, is a generator. So there's a lot of very beautiful mathematics connected with this little bit of group theory. And let me just give one sort of corollary of Lagrange's theorem. Let G be a group. Let A be an element of G, and let H be the cyclic subgroup generated by H. What's called the order of A is the number of elements in H. Also, it's the smallest number K, positive integer K, such that A to the K is equal to 1. And by Lagrange's theorem, the order of H divides the order of G. So the order of the element A, which is the number of elements in the cyclic subgroup it generates, the order of A divides the order of G. So the order of an element of a finite group always divides the order of the group. So I claim from this little bit of group theory, I can prove Euler's theorem. So this is a proof that Lagrange's theorem implies Euler's theorem. So let G be the multiplicative group of congruence classes mod M that are relatively prime to G. So this is a finite group of order phi of m. Their phi of m congruence class is relatively prime to m. That a be an integer, which is relatively prime to m. So then a plus mz is a congruence class in G. And then this have order D. So D divides phi of m by Lagrange's theorem. The order of an element divides the order of the group. A plus mz is an element in this group G. The group G has order phi of m, so a plus mz has order D. So that means a plus mz raised to the dth power is 1 plus mz. Or a to the d plus mz equals 1 plus mz. Or a to the d is congruent to 1 mod m. If d divides phi of m is d times q. So a to the phi of m is a to the d times q. This is a to the d raised to the power q, but a to the d is 1 mod q. So this is congruent to 1 to the q, or 1 mod m. I just proved Euler's theorem. A to the phi of m is congruent to 1 mod m. That's pretty good. Well, anyway, there's a lot here to chew on and think about. This is as far as we go in chapter 2. If you look at the syllabus, the exam on chapter 2 is a week from today. Monday's class is all review. The best way to study for the exam is just to study the homework problems and the proofs, but all the numerical problems will be like homework problems. And I have a lot of office hours scheduled. I have office hours every day this week, in fact.
Professor, can you post the office hours link and also the time, because I've been looking in Blackboard, I didn't find it.
It's on Blackboard under
The
announcements.
dates?
Yeah.
Okay.
I posted the office hours over the last weekend for Monday, Tuesday, Wednesday, and Thursday. And I'll post an office hour for Friday also. And when I do that, I'll make sure I send out an email just to make sure everybody has it.
Yes, please, because yesterday I entered to Blackboard to see the time and I didn't find it.
Yeah, I'm pretty sure it's there, but I'll double check. I'll make sure it's there.
Thank you.
Okay. Any other questions?
Professor, in Monday you're gonna tell us like the topics that will be included on the exam?
Everything on the syllabus.
Everything so far is like including the first exam also?
Well, I won't have questions explicitly from the first exam, but no, the exam is really going to be on chapter 2. But
Okay.
if in order to solve a problem, you need to know something from chapter 1, then I assume you know that. But all the questions will be on congruences.
Yeah, that makes sense. Okay, thank you,
Yeah.
Professor.
Professor, I got a question also.
Sure.
It's about the homework on Blackboard. On the assignments, the homeworks are from lesson 1 to 11. lesson 11 is the last homework
Oh.
available on Blackboard. That's from last week.
Oh, I'll go as soon as I'll go correct that as soon as we log off right now.
Now, the homework that was due last Monday. How are we supposed to submit that?
I'll change the date. It won't be late. In any case, there's not a penalty for submitting the homework late. It's the date is just to try and encourage you to stay up to date.
All
But
right.
no problem about that. Okay. All right, that's all. See you soon. Bye all.
Have a good day, Professor.